Graphs of exponential functions. As we discussed in the previous section, exponential functions are used for many real-world applications, such as finance, forensics, computer science, and most of the life sciences. Working with an equation that describes a real-world situation gives us a method for making predictions. Most of the time, however, the equation itself is not enough. We learn a lot about things by seeing their pictorial representations, and that is exactly why graphing exponential equations is a powerful tool. It gives us another layer of insight for predicting future events. Graphing exponential functions. Before we begin graphing, it is helpful to review the behavior of exponential growth. Recall that the table of values for a function of the form f of x equals b to the x power, whose base is greater than 1. We will use the function f of x equals 2 raised to the x power. Observe how the output values in table 1 change as the input increases by 1. Each output value is the product of the previous output value and the base 2. We call the base 2 the constant ratio. In fact, for any exponential function with the form f of x equals ab to the x power, b is the constant ratio of the function. This means that as the input increases by 1, the output value will be the product of the base and the previous output, regardless of the value of a. Notice from the table that the output values are positive for all values of x. As x increases, the output values increase with bound, and as x decreases, the output values grow smaller, approaching 0. Figure 1 shows the exponential growth function of f of x equals 2 to the x power. The domain of f of x equals 2 to the x power is all real numbers. The range is 0 to infinity, and the horizontal asymptote is y equals 0. To get a sense of the behavior of exponential decay, we can create a table of values for a function of the form f of x equals b of x, whose base is between 0 and 1, and we'll use the function g of x equals half raised to the x power. Observe how the output values in table 2 change as the input increases by 1. Again, because the input is increasing by 1, each output value is the product of the previous output and the base, or the constant ratio half. And notice that from the table, the output values are positive for all values of x. As x increases, the output values grow smaller, approaching 0, and as x decreases, the output values grow without bound. Figure 2 shows the exponential decay function g of x equals half raised to the x power. The domain of g of x equals half raised to the x power is all real numbers. The range is 0 to infinity, and the horizontal asymptote is y equals 0. Characteristics of the graph of the parent function f of x equals b to the x power. An exponential function with the form f of x equals b to the x power, b is greater than 0, b does not equal 1, has these characteristics. One-to-one function, horizontal asymptote y equals 0, domain negative infinity to infinity, range 0 to infinity, x-intercept none, y-intercept 0, 1, increasing if b is greater than 1, decreasing if b is less than 1. Figure 3 compares the graphs of exponential growth and decay functions. How to? Given an exponential function of the form f of x equals b to the x, graph the function. 1. Create a table of points. 2. Plot at least 3 points from the table, including the y-intercept 0, 1. 3. Draw a smooth curve through the points. And 4. State the domain, negative infinity to infinity, the range 0 to infinity, and the horizontal asymptote y equals 0. Graphing transformations of exponential functions. Transformations of exponential functions have similarity to those of other functions. Just as other parent functions, we can apply the 4 types of transformations: shifts, reflections, stretches, and compressions. To the parent function, f of x equals b to the x power without loss of shape. For instance, just as the quadratic function maintains its parabolic shape when shifted, reflected, stretched, or compressed, the exponential function also maintains its general shape regardless of the transformations applied. Graphing a vertical shift, the first transformation occurs when we add a constant d to the parent function, f of x equals b to the x power, giving us a vertical shift d units in the same direction as the sign. So for example, if we begin by graphing a parent function, f of x equals 2 to the x power, we can then graph two vertical shifts alongside it using d equals 3, the upward shift, g of x equals 2 raised to the x power plus 3, and the downward shift, h of x equals 2 to the x power minus 3. Both vertical shifts are shown in figure 5. Observe the results of shifting f of x equals 2 to the x power vertically. The domain is negative infinity to infinity remains unchanged. When the function is shifted up 3 units to g of x equals 2 to the x power plus 3, the y-intercept shifts up 3 units to 0, 4. The asymptote shifts up 3 units to y equals 3. The range becomes 3 to infinity. When the function is shifted down 3 units to h of x equals 2 to the x power minus 3, the y-intercept shifts down 3 units to 0, negative 2, and the asymptote also shifts down 3 units to y equals negative 3. The range becomes negative 3 to infinity. Graphing a horizontal shift, the next transformation occurs when we add a constant c to the input of the parent function, f of x equals b to the x power, giving us a horizontal shift c units in the opposite direction of the sign. For example, if we begin by graphing the parent function, f of x equals 2 to the x power, we could then graph two horizontal shifts alongside it using c equals 3. The shift left, g of x equals 2 to the x power plus 3, and the shift right, h of x equals 2 to the x minus 3 power. Both horizontal shifts are shown in figure X. Observe the results of shifting f of x equals 2 to the x power horizontally. The domain equals negative infinity to infinity and remains unchanged, and the asymptote y equals 0 remains unchanged. The y-intercept shifts such that when the function is shifted left 3 units to g of x equals 2 to the x plus 3 power plus y-intercept becomes 0, 8. This is because 2 to the x plus 3 power equals 8 multiplied by 2 to the x power, so the initial value of the function is 8. When the function is shifted right units to the h of x power equals 2 raised to the x minus 3 power, the y-intercept becomes 0, 1/8. Again, see that 2 raised to the x minus 3 power equals 1/8 multiplied by 2 to the x power, so the initial value of the function is 1/8. Shifts of the parent function, f of x equals b to the x power. For any constant c and d, the function f of x equals b raised to the x plus c power plus d shifts the parent function f of x equals b to the x power. Vertically d units in the same direction of the sign d. Horizontally c units in the opposite direction of the sign of c. The y-intercept becomes 0, b to the c power plus d. This horizontal asymptote becomes y equals d. And the range becomes d to infinity. The domain is negative infinity to infinity, remains unchanged. How to? Given a exponential function with the form f of x equals b raised to the x plus c power plus d, graph the translation. 1. Draw the horizontal asymptote y equals d. 2. Identify the shift as negative cd. Shift the graph of f of x equals b to the x power left c units if c is positive and right c units if c is negative. 3. Shift the graph of f of x equals b to the x power up d units if d is positive and down d units if d is negative. And 4. State the domain, negative infinity to infinity. The range is d to infinity, and the horizontal asymptote is y equals d. Stretches and compressions of the parent function f of x equals b to the x power. For any factor a greater than 0, the function f of x equals a multiplied by b to the x power. Is stretched vertically by a factor of a if the absolute value of a is greater than 1. Is compressed vertically by a factor of a if the absolute value of a is less than 1. Has a y-intercept of 0a. Has a horizontal asymptote at y equals 0. A range of 0 to infinity, and a domain of negative infinity to infinity, which are unchanged from the parent function. Reflections of the parent function f of x equals b to the x power. The function f of x equals negative b to the x power. reflects the parent function f of x equals b to the x power about the x-axis, has a y-intercept of 0, -1, has a range of -infinity to 0, has a horizontal asymptote at y equals 0, and a domain of -infinity to infinity, which are unchanged from the parent function. The function f of x equals b raised to the -x power, reflects the parent function f of x equals b raised to the x power about the y-axis, has a y-intercept of 0, 1, a horizontal asymptote at y equals 0, a range of 0 to infinity, and a domain of -infinity to infinity, which are unchanged from the parent function. Summarizing translations of the exponential function. Now that we have worked with each type of translation for the exponential function, we can summarize them in Table 6 to arrive at the general equation for translating exponential functions. Translations of exponential functions. A translation of an exponential function has the form f of x equals a multiplied by b raised to the x plus c power plus d, where the parent function y equals b of x, b is greater than 1, is shifted horizontally c units to the left, stretched vertically by a factor of the absolute value of a equals the absolute value of a greater than 0, compressed vertically by a factor of the absolute value of a if 0 is less than the absolute value of a less than 1, shifted vertically d units, reflected about the x-axis when a is less than 0, and note the order of the shifts, transformation, and reflections follow the order of operations. 6.3 Logarithmic functions. In 2010, a major earthquake struck Haiti, destroying or damaging over 285,000 homes. 1 year later, another stronger earthquake devastated Honshu, Japan, destroying or damaging over 332,000 buildings, like those shown in Figure 1. Even though both caused substantial damage, the earthquake in 2011 was 100 times stronger than the earthquake in Haiti. How do we know? The magnitudes of earthquakes are measured on a scale known as the Richter scale. The Haitian earthquake registered a 7.0 on the Richter scale, whereas the Japanese earthquake registered a 9.0. The Richter scale is a base 10 logarithmic scale. In other words, an earthquake of magnitude 8 is not twice as great as an earthquake of magnitude 4. It is 10 raised to the 8th power minus 4 equals 10 to the 4th equals 10,000 times as great. In this lesson, we will investigate the nature of the Richter scale and the base 10 function upon which it depends. Converting from logarithmic to exponential form. In order to analyze the magnitude of earthquakes or compare the magnitudes of two different earthquakes, we need to be able to convert between logarithmic and exponential form. For example, suppose the amount of energy released from one earthquake were 500 times greater than the amount of energy released from another. We want to calculate the difference in magnitude. The equation that represents this problem is 10 to the x power equals 500, where x represents the difference in magnitudes on the Richter scale. How would we solve for x? We have not yet learned a method for solving exponential equations. None of the algebraic tools discussed so far is sufficient to solve 10 to the x power equals 500. We know that 10 to the second equals 100, 10 to the third equals 1,000, so it is clear that x must be some value between 2 and 3, since y equals 10 to the x power is increasing. We can examine a graph, as in Figure 2, to better estimate the solution. Estimating from a graph, however, is imprecise. To find an algebraic solution, we must introduce a new function. Observe that the graph in Figure 2 passes the horizontal line test. The exponential function y equals b to the x power is 1 to 1, so its inverse, x equals b to the y power, is also a function. As is the case with all inverse functions, we simply interchange x and y and solve for y to find the inverse function. To represent y as a function of x, we use a logarithmic function of the form y equals log base b of x, and the base b logarithm of a number is the exponent by which we must raise b to get that number. We need a logarithmic expression as the logarithm with base b of x is equal to y, or simplified log base b of x is y. We can also say b raised to the power of y is x because logs are exponents. For example, the base 2 logarithm of 32 is 5 because 5 is the exponent we must apply to 2 to get 32. Since 2 to the 5th power equals 32, we can write log base 2 of 32 equals 5, and we read this as log base 2 of 32 is 5. We can express the relationship between logarithmic form and its corresponding exponential form as follows. Because logarithm is a function, it is most correctly written as log base b of x. Use parentheses to denote function evaluation, just as we would with f of x. However, when the input is a single variable or number, it is common to see the parentheses dropped in the expression written without parentheses as log base b of x. Note that many calculators require parentheses around the x. We can illustrate the notation of logarithms. And notice that comparing the logarithm function and the exponential function, the input and output are switched. This means y equals log base b of x and y equals b to the x power are inverse functions. Definition of the logarithmic function. A logarithm base b of a positive number x satisfies the following definition. For x greater than 0, b greater than 0, and b not equal to 1, y equals log base b of x is equivalent to b of y equals x, where we read log base b of x as the logarithm with base b of x, or the log base b of x. The logarithm y is the exponent to which b must be raised to get x. And also, since the logarithmic and exponential functions switch the x and y values, the domain and range of the exponential function are interchanged for the logarithmic function. Therefore, the domain of the logarithm function with base b is 0 to infinity, and the range of the logarithm function with base b is negative infinity to infinity. Converting the exponential to logarithmic form. To convert from exponents to logarithms, we follow the same steps in reverse. We identify the base b, exponent x, and output y, then we write x equals log base b of y. Evaluating logarithms. Knowing the squares, cubes, and roots of numbers allows us to evaluate many logarithms mentally. For example, consider log base 2 of 8. We ask, to what exponent must 2 be raised in order to get 8? Because we already know 2/3 equals 8, it follows that log base 2 of 8 equals 3. Now consider solving log base 7 of 49 and log base 3 of 27 mentally. We ask, to what exponent must 7 be raised in order to get 49? And we know that 7 squared equals 49, therefore log base 7 of 49 equals 2. And we ask, to what exponent must 3 be raised in order to get 27? We know 3 to the 3rd power is 27, therefore log base 3 of 27 equals 3. Even some seemingly more complicated logarithms can be evaluated without a calculator. And for example, let's evaluate log base 2/3 of 4/9 mentally. We ask, to what exponent must 2/3 be raised in order to get 4/9? Well, we know 2 to the 2nd power equals 4 and 3 to the 2nd power equals 9. So 2/3 raised to the 2nd power equals 4/9. Therefore, log base 2/3 of 4/9 equals 2. Definition of common logarithm. A common logarithm is a logarithm with base 10. We write log base 10 of x simply as log of x. The common logarithm of a positive number x satisfies the following definition. For x greater than 0, y equals log of x is equivalent to 10 to the y power equals x. We read log of x as the logarithm with base 10 of x, or log base 10 of x. The logarithm y is the exponent to which 10 must be raised to get x. And the definition of natural logarithm. A natural logarithm is a logarithm with base e. We write log base e of x simply as natural log of x. The natural logarithm of a positive number x satisfies the following definition. For x greater than 0, y equals the natural log of x is equivalent to e to the y power equals x. We read the natural log of x as the logarithm with base e of x, or the natural logarithm of x. The logarithm y is the exponent to which e must be raised to get x, and since the functions y equal e and y equal natural log of x are inverse functions, natural log of e to the x power equals x for all x, and e equals x for x greater than 0. Access this online resource for additional instruction and practice with logarithms. Introduction to Logarithms, openstackscollege.org.